All right, well, here we go. Another 4 weeks. Another subject. We turn the corner. So now we're going to talk about AC, alternating current. So there, I made a little circuit. So alternating current. Well, first we had direct current. I think I did this with direct current, didn't I? Put something up on here. So direct current is like a battery. What is battery? Where the voltage is pretty much constant until the battery starts dying. And the current would be pretty much constant as long as we're not changing loads or resistance. But we talk about alternating current. It alternates. And it's funny that we call it alternating current because they could have called it alternating voltage as well. Because I have graphed here the voltage on this. The voltage goes up. Here's 0. It goes to a peak, and then it goes back down to a negative. Then it goes back up to a positive. Then it goes to a negative. And I think we discussed that in meters was our first little trip into that. So alternating current. Let's see, 1. Alternating current, AC, or alternating current. Sometimes I don't like this new thing.
Well, we can read it.
What?
Well, we can read it.
You can. I'm still learning how to use it. There we go. Hey, okay, so alternating current theory. So theory. Or Y, let's see where that's going to put it. No, that's going to put it down there. That is not where I wanted it. I want it over here. There we go. Alternating current theory. Oh, I see. I'm hitting. I'll just leave and then we'll come back in a little bit. Try this again. There we go. All right. Point number A. Current that periodically changes direction and continuously changes in amplitude. That's as opposed to DC that never changes direction or magnitude. DC never changes. So going back to this, current that periodically changes direction. So from this to this is, well, this whole point from right here to right over here, that is the positive direction. So if we were to color code this, not for you because you color code things different, but we're going to color code it. What color would this be from this point to this point?
Red.
Red, so it's positive and red. And from this point to this point it is black, and it's swinging negative. So, all right, so we have it changing direction. Let me see. So, there we go. As opposed to DC, opposed to DC, that never changes. Direction never changes direction or amplitude. I'm just going to leave it with direction. Never changes direction. That's more accurate. All right, so.
So it's like AC is grabbing the shoulders of the electrons and shaking them?
Yes. Let's see. Oh, that should be B. So there we go. B. All right, B. True DC. True direct current. Actual down to if you took an oscilloscope like I was just looking at with the waveform, and if we looked at DC and we zoomed way in. So when you're looking at an oscilloscope, we have amplitude here, voltage there, and the time over here. So if we scrolled like way in, you can see that Well, if you go far enough with this AC, what does it look like? It looks flat because we're looking at 19.888.50842 to 19.888.50842 seconds. So I mean that is just okay, but oops, no, can't do that. Go back the other way. Go back. There we go. Now if we took DC and did that with a battery and zoomed way in on a battery, we would see it look like that. It'd be straight. Because it starts out straight, it is straight. But if we took anything else, an inverter or something like that, and we zoomed way in, we'd see it's kind of wavy. Because everything else but a battery is taking AC and converting it to DC. So battery starts out DC and stays DC. Everything else that I can think of starts out as AC and is converted to DC if we want it. Like those little DC, you did the motor project. So you brought over the power supply. What did that start out as? We plugged it in the wall, didn't we?
AC.
So if we put a oscilloscope on that, we would find out that it's not perfect DC. I mean, it's DC, but it's not perfect. So true DC is only created with a battery. Maybe true DC, but I should. There we go, buttery. Not true DC, maybe perfect DC would be a better term to use. All other electricity produced. Produced with all other electricity produced. Well, I'll just go with it. With mechanical means. What does mechanical means?
Piezoelectric.
Okay. I don't know about that one. I was thinking alternators, generators.
Oh.
Is AC converted to DC?
Solar panel also?
Well, that's not mechanical.
Okay. Yeah.
But you are right. I believe solar panels are all DC, right? I think they are. That's why they have a big inverter to convert it to AC. Hadn't thought of that.
So that is true DC. Could that be considered true DC then? Could you run
Yeah.
a DC stuff off of your solar panels? No
Yeah.
problem?
Yeah, pretty sure.
So then true DC
Yeah.
is not only created with a battery.
I don't know. I hadn't thought of that. Well, solar's pretty new. With DC or solar. There we go. I'll add to it.
Maybe back in the day, it was just batteries, but nowadays.
Yes.
I'm sorry.
I'll add that on here.
I ruined it.
You ruined it. I'm done. It's a good question. All right. AC has advantages. Advantages of AC. Let me get this back over here. AC advantages. And there are many. There was a really good movie I watched on an airplane once, and it was something about, it was the fight for electricity in America, where they had Westinghouse, Nikola Tesla, and Edison. Yeah. Current Wars, that's it. Yeah. Yeah, I like that. That was a good movie. And there was a big fight about should they go DC or AC, and some political wranglings in there. And according to the movie, I think it's true, who'd they get to build? One of them they convinced them to build the electric chair. And then they used the electric chair to prove, because they used DC to prove that that's what would kill people, and that AC wasn't as deadly. But all right, I don't know about that. So anyway, I. So voltage can easily be changed by transformers. Voltage can easily be changed by transformers. Not the robots in disguise, but the but the other ones, I know. I thought this is finally it's going to get cool around here. No. We can use transformers. This would be a transformer. That's a coil. That's a core, iron core, and another transformer with maybe a lot more wires. And we'll get into this next week, but basically what happens with AC voltage, because it's constantly changing, that in a transformer, you have in a coil of wire a magnetic field being built up by AC. Well, DC would too. It'd build up and it just stays built up. But with AC, it builds up and collapses, builds up and collapses, builds up and collapses in this first coil. We'll call that coil number 1 so you can see. And so as that, every time it builds this magnetic field grows, and those magnetic lines of flux cut across the secondary one. And like I said, we will get more into this in the next few weeks. But that flux, the current in one produces a magnetic field that grows and shrinks and grows and shrinks. And that magnetic field passing across the wires inside 2 is magnetic fields crossing a wire. Whenever you have magnetic fields and wire with relative motion, you have electricity. And so what it does, it takes a little bit of voltage over here, and if you have a whole bunch of current windings over here, it's going to step up the voltage. Anyway, that's next week's stuff. But without AC, you have a hard time doing that. You'd have to use chopped DC, which is kind of weird. AC can be produced. Oops, I forgot about this. Got the right pin. Let's see. AC can be produced in three-phase systems. That's phase, not whatever that word is. Three-phase systems. All right. Three-phase systems. Let's see. Allowing the use of smaller motors. Three-phase. Let me fix this a little bit. Phase systems, use of smaller motors. Maybe if I did this. Gives me a little bit of room to write over here. All right. So in. There we go. So if I did that right, close enough, this is my 0 voltage mark right here. So I have the positive, negative. That would be a single phase, what we get out of our wall. But when we look at three-phase, also called polyphase, and I'm probably not going to do this right, they have each one of the phases is out of sync with the other one, but yet somewhat in sync. Not the boy band, but I need another color, black. All right. And so what it looks like, I didn't draw it too well, is you'll have peaks spaced evenly apart. And so rather than have this long period of time before you get to another peak, from the peak here to the peak down here, peak here to peak down here, you'll have peaks stacked evenly all the way across. And so you're getting like three phases, so you're getting 3 pulses. And so you can make the motor much smaller. And so you'll see that done with a lot of shop equipment. Will be 3-phase. Let's see, smaller motors.
Is that because it's like kind of like juicing it up? It's got
Juicing
like
it.
more power, and so you don't need as big of a motor to get the same amount of power.
Yep. AC generators are more efficient. more efficient than DC generators. And I like this one. Wire used in AC. Wire used in AC can be much smaller.
So like smaller gauges.
Exactly. Would you think it means shorter?
Yeah.
Yeah, you use as long a wire.
Yeah, you use much shorter wire. Size can only be figured out two ways, either width or length. So yes, I would be talking about the width.
You need only 8 feet of wire, but it's AC, so you need
So,
7. Bluetooth.
All right. Yes, Bluetooth wire can be much smaller.
Just an arc from
Smaller due to sometimes smaller. Due to increased voltage. Voltage. Hey, there we go. All right, so I have an example. And just for punishment for myself, I will write it out. So a 1 horsepower, that's a 1 horsepower motor. How many watts is 1 horsepower motor? 746. Seven 746 watts at 60%. You knew I was going to do that. Efficient. Driven at a distance of 100 feet from source voltage of 10 feet. We'll need oops, 10 foot will require, well, hang on. 10 feet will require how many amps? 12 is very close, 125 amps. So if I wanted to know what size wire, what would I do?
Go to the chart.
Go to the chart.
11.2.
So I would go to, on the top, 125 amps, scroll down until I got to
10 feet.
10 feet, and roll down until I got to
Gauge wire.
gauge wire. Would be a number 1 wire. So I do number 1 wire, weighing 25 pounds. That's 100 feet of 25 wire. Weigh 25 pounds. I got this example out of a book somewhere, so if it's wrong, don't blame me. I didn't make it up.
Is that source voltage of 10 feet?
100 feet from the source voltage of 10 feet. So the wire length is 100 feet. The source, it's a 10 volt battery, 1 horse motor, 60% efficient, needs 125 amps.
The 10 volts. Source
10 volts.
voltage of 10 volts.
Yeah.
okay, it was just confusing where it says like feet right after it.
Driven at a distance of 100 feet from source voltage of 10 feet. Oh, I'm sorry. That doesn't.
So confused.
That's what it is. Voltage of 10 volts. Will require 125 amps. There we go.
AC is totally
Source
different.
voltage.
Well, that's different. That's another lesson. We'll get into converting voltage to feet.
A voltage of 10 frog feet.
So same thing using a 200 volt AC. I'm not sure. Yeah, I didn't think it was going to work out. 200 volt AC. System will need 5 amps, which uses a number 18 wire. This sounds too good to be true. Weighing 1 pound. That's some significant weight savings. Oh yeah, I remember what I'm doing now. All right, so how is that should be a 2, whatever. How is AC produced? How is, huh?
How many pounds is it weigh?
1. Well, it didn't do the 1 there.
So on number 1 of that example, that's a DC system versus number 2 is an AC.
Correct.
Okay.
That's why it says AC right there,
Yeah.
and there's 10 volts. So, okay. How is AC produced? How is AC produced? Well, that's a really good question. I'm so glad you asked. Let me see. We will go to, let me see what I want. I want that over there. Stop. There we go. I want that. I want, let me see. There we go. We will use this to start our discussion. So I'm going to go through this PowerPoint. You'll have to take notes on this because I'm not going to write all the notes back and forth. All right, enable content. Yes. Slideshow. From beginning. All right, alternating current. Oh, there we go. I forgot to put that in there. There's my red line direct current. There's alternating current. That's 1 cycle from here to here. We'll get into that in a little bit. How is voltage induced in a conductor? Well, we need 3 items to generate current flow.
A load, voltage supply.
You're thinking of what does it take to make a circuit.
No.
I'm talking about what does it take, 3 things to generate current flow. I had them right here. What's that?
Coil, magnet, and motion?
Very up. Magnetic field. A conductor. And relative motion. So if I had a magnet, ooh. You write that down. I'm going over it.
All right, see you in 10.
There it is. I have here nothing more than some crap I found in the garage. I have some magnets inside there. Then I took some coroplast plastic and I put a nail in there, and so I can rotate the magnet around and just put some wire and a little light bulb. And if it still works, turn the lights off real quick. See the little light goes on. So it's nothing more than just me. Magnets. Lights on. Magnets. Conductor and relative motion. Well, if I did it like this, and this is my, I had a magnet, I went like that, would that work?
Yeah.
It would. What's the problem with that, though?
It's inefficient.
Well, that's pretty inefficient. So, yeah, problems with that. Well, it's not very practical to do that all day long. So, solution is, and this is how we get into generators. There's a picture of a little generator up there. So, generators, alternators, all that kind of stuff. We're basically talking about a generator right now. We're going to, now this right here uses magnets that rotate with wire that is stationary. In this example, as in a generator, and we're going to look at this again when we get into generator, so this is the precursor to that, is we're going to leave the magnet stationary and we're going to take wire and we're going to rotate the wire. So in this particular case, and it's kind of important that, and unfortunately if you're watching the video, my picture is like right down here and it's kind of blocking it, so maybe I can fix that. I don't know if I can. Hang on. Try to be nice about this. No, I can't, so. All right. Another day. All right, so we look at this armature right here, and that's what that's called. The armature is the loop of wire. And we'll notice that this top loop, get a laser pointer, this top loop right here, and this is important, it comes back to this point right here. That's a slip ring. So it's welded or soldered, if you like, to that slip ring. And right here, this little square block, that is a piece of carbon. So we have a tube with a carbon against it, so current can transfer through that. Then we'll look at this bottom part of the loop, comes all the way back here to the back slip ring, or this slip ring right here, if you can see that okay. And another carbon brush, then we have our load right there. So loop of wire, add brushes, rings, and we rotate. So as we rotate this, what you'll notice is that we have the south magnet and the north magnet, and that is going to rotate around, and we're going to take a look and see what happens to each side. So, all right, problems. Well, you don't know it yet, but if we were creating a DC generator, which is what this slide is really doing, this will produce AC, not DC. So again, I'm using a PowerPoint off of a DC generator to explain how a DC generator works. But I'm going to stop it before we get into the DC part. Right now I'm showing you how AC is made. So if this were a DC generator, this would not work for a DC generator because it makes AC, which is what we want to know how it works. So the way it makes AC and why it makes AC is because we have in there these magnets, right? And as this says right here, the greatest voltage occurs as the conductor passes at right angles to the lines of flux. So we have a north magnet and a south magnet, and the two are attracted to each other. And in between them, we have magnetic lines of flux going, well, not back and forth, goes from the north to the south, actually, in theory. So we have these, and maybe you can see these little blue lines right in there represented. They're kind of far apart up here, and then down in the middle, they get closer together where it's really concentrated, these lines of magnetic flux. That's the attraction between the north and the south. And when we have that loop of wire that goes through there, represented by these red dots here, as that loop of wire is going this way, we have one coming, am I doing it backwards to you? Down on the north and up on the south, right? Okay, so right there, what we say is those conductors are cutting the magnetic lines of flux. They're cutting through. That is relative motion of a wire through a magnetic field. That produces current. Okay, but that loop of wire is eventually going to do this, and it's going to be on top. I think that might be my next slide. If it's not, it should be. So eventually now it's up there. Now when it's doing this right here, it's not cutting those lines of flux, it's running parallel to them. So that's going to produce zero voltage.
So like, bet you can feel it kind of on motors. Some motors.
Sometimes, yeah, you could. Yeah, it
feel
feels
it
almost like a
kinda-
little piston going up and down. It's like compression, no compression. What's going on? That's what it is. So it makes it a little bit harder when it's down here. So all right. So the least voltage occurs as a conductor passes parallel to the lines of flux.
So this, when it said it's least, that's when it is hitting its zero, basically, when it's coming back to center.
This is the zero position. Okay. Again, I don't do. I never ask you to memorize hand rules of thumb, but it's relevant to our discussion to say that to determine the direction of current flow, we must use the left-hand rule. Excuse me. The thumb points in the direction of motion. The pointer points in direction of the field from north to south. That's the field of the magnet. And then this is the current flow. Middle finger points in the direction of current flow. So if you can do that, everybody's cool with that? That's our new gang sign. So we're down the street, you just kind of, right? Ohm's law, yo. Okay.
Ohm's enforcers.
Yeah.
Ohm's lawyers.
All right. So using the left-hand rule of thumb, yes.
What do you mean in the direction of motion?
Well, I'm gonna show you.
Oh, okay.
Step, right?
One point
Well, I'm going to depend on you.
Motion, pointer's field, middle is current.
Which one? That one. That one right there is the current flow. Not this one, not that one. It's that one right there. All right. Left-hand rule. Which way will the current flow? All right. Direction of movement. So, direction of movement. It's current flow. This is the magnetic from north to south. If I remember correctly, this is really hard to do. Direction of, so
Towards, yeah.
out the board?
Yeah, outboard.
Okay, you see what I'm doing there?
Yep.
Out the board. We go out the board, went out the board. See? Direction of movement of the wire. I'm moving the wire up. From north to south, because we always say that lines of flux go from north to south. And then which way does the current flow? That way, negative to positive. And honestly, that's why I don't ask you to memorize rules of thumb, because then it's like, well, is it the rule of, if we did rule of thumb and we use conventional flow, then it'd be different. So it just gets to be too much. But I want you to remember that for just at least the next 4 and 5 minutes. And then you can be like done with it. All right. So knowing that, this is where this is going to get rather important. So applying the left-hand rule of thumb, segment A. So segment A is down over here. Segment A moves up. So if it's moving up, then current, and then we have from north to south. See, this is, do that, up, north to south, anyway. Using the left-hand rule of thumb, segment A is moving up. Using that, current will flow across the load from point 1 to point 2. So it's going this way. Current is flowing this way. And what I want you to know is, why is it flowing that way? That's all I'm asking you to know. It's flowing this way for a reason, and that reason is because of the relative motion left-hand rule of thumb. Follow, everybody? Okay. Now, segment, so we'll go back. Okay, so segment A is over here. And of course, segment B would be just the opposite. It's still going to go with it. You can't have them doing this. That wouldn't work, right? So segment B is going to play along. We're just going to go that way. So segment A is moving up. Segment B is moving down. So it's all going to kind of, but then the north and the south, anyway, it's going to work out so that it's flowing from A around to B. It's going through this slip ring, through that brush, through here, down, back to the brush, back through A, and looping around.
So as that loop armature changes, that's where we're getting our waves.
Yes. So now we're going to watch what happens. So A is going to be on your left, and now A is on the right. So left to its own devices here, using the left-hand rule of thumb. Now B is over here, so it comes around. It's still going the same way, right? Still going through the loop this way. But B comes around to A, and A comes all the way now. A comes to here and through, and now it's got to go this way because A is now on the other side. See if I go back one. See, A is right here, going through this way, and B is this way. So B, A. So all right, so now it goes the other way.
Go
So,
back again one more.
well, there's the two side by side. Yes.
So are the brushes applicable to, are they specific to it being a DC?
No,
Generator
it's not
for-
even relevant at this moment.
Okay, I saw brushes on that old generator I showed you before, and they had DC brushes.
No,
but they
brushes
were
are
just-
brushes.
They were just there. They weren't attached to anything.
Yeah. Okay, so you can see that's both of these put side by side with the A loop here coming around this way, comes to B, out, down, this way, comes around A, B, now it comes all the way down here and out, so it goes backwards through the resistor. So it's going this way, then that way, then this way, then that way, and because of the left-hand rule of thumb. Everybody follow me so far? And that's the why. All right, let's see. What did we just learn? The greatest voltage is produced as the conductor moves at right angles to the line of flux. We already said that, right? The left-hand rule shows this current is reversing directions. Then we can understand the following. There we go. So kind of putting it all together, when the loop of wire is straight up and down,
Zero.
that is zero, and that corresponds to this right here. We have zero voltage. And then as it starts to rotate around and the loop of wire comes perpendicular to the lines of flux and cuts the lines of flux, that is the maximum right there. And then it's going to turn around and keep going, and then it gets back to here again, then it's zero. Then it goes this way and it reverses itself. So right here, it's coming out this way, reverses, goes back that way, and that's the drop off right here,
It's the valley.
the valley. Well, this is an upside down valley. All right, and then if we look at this, we're going to look at it in degrees of rotation. If we start here at 0, this is
90,
90 degrees, then
180,
180 is back to 0, then
270.
and then 360 all the way around.
It's like trying to do the arms of a clock right there.
Yeah. Oh, that's for another time.
Oh.
It's vector.
Oh yeah.
Oh yeah. Okay. Back to this. So, how is APCs produced? Well, let's see. What did we cover here?
Magnetic field, conductor, relative
Okay.
motion. By putting your phone in there.
Stick your thumb there.
All right, 2, which is really 3 because of the way the program decided it wants to do this. Let's talk about waveforms. Waveforms. All right, we have many types. Let's go with this pen. Hell with it. All right, so we have DC, which is straight. So this is looking at the picture of our voltage or amperage on an oscilloscope. What would that look like? So there's DC. We have chopped DC. Which would kind of look like this. I don't like that. I don't like that.
It's like a shunt.
Looks more like that, I think.
Where you're alternating between off and on states.
Yeah, but it'd be so close together that you just see DC,
Okay.
pretty much. And then, of course, we have the AC, which is what we've been talking about, which has a, if this is the 0 plane, it's going to go above the 0 plane, an equal amount below the 0 plane, and on and on and on. All right, so we're going to look at that just a little bit more. All right, one cycle of AC is from 0 to maximum to max in one direction, returns to 0, increases to a maximum in opposite direction, and returns to 0. Well, that's one way of saying it. Another way of looking at it really is, if we can look at this waveform. If I said that, what is one cycle? Well, I said it was from 0 to a maximum, back to 0, and then back around to 0. So it is a complete cycle. We could really do the same thing from right here. So from this point down and up to the same point, that's a cycle too. So as long as you're measuring the same thing. One cycle is not from 0 to 0. See, that would be one graticule in this case, one block. From here to here, let's see if I can...
So they call it a cycle because it's like...
The complete up and down.
Because it's a complete rotation.
Complete rotation from wherever you started of that loop of wire. You just pick where you want to start, and as long as it's all the way around. There you go. So one cycle's all the way through. Let me see.
Would a 3-phase be 3 separate loops of wire spinning?
Yes, it would.
Okay.
I wonder if...
On the same magnet? Guess so.
I have not messed with this enough to know if I could do 3-phase Y. I don't know. I'll screw it all up. I don't think I can. Frequency. Phase. Well, it has 0 phase. I don't think that's it. Nah.
That might be like
That's degrees.
if it's out of
It's
phase,
phase
or
angle.
phase.
So that's your phase angle. Oh. All right, back to grapher. All right, so there we go. I just like it's a good wave right there to look at. But I could add another one of those generators probably to it, change the phase. Anyway, okay. Let's see, what do I got here? All right, let's see. The number of cycles. Let me see. I think I can. Let's try this. The number of these cycles per second is the frequency. And it's a shame we don't have anybody named Kenneth in here to ask the frequency. Is the frequency that is also called, aka, the hertz.
The symbol is just HZ, right?
The symbol is HZ.
Ah, it hurts.
I guess that comes from the auto rental company, right?
I was trying to work it in. And then it was going to go with an O.J. Simpson reference, and then I was going to say, thank God that Tony's in here because he's my age and we're contemporaries, and he would understand my jokes. The rest of them go, why are they bringing up O.J. Simpson? Right. O.J. Simpson used to be the spokesperson for Hertz Rent-A-Car before he got into a little bit of trouble with a lady named Nicole.
Gloves don't fit.
All right. All right. 1 hertz is 1 cycle and 1 second. So 1 hertz. 1 hertz is 1 cycle. That's not going to work out. One cycle in 1 second.
Aren't most outlets rated for like, or aren't most outlets outputting like 60 hertz or something like that?
Man, he's just right. It's like you read my notes right here. But I wish I had the outline running, so let's try it. I period. There we go. Who knows what will happen. Standard U.S. electricity. Standard U.S. electricity is 60 hertz. Is 61.4 HZ, 60 hertz.
Other countries are 59.
Yeah, we're just like, we're better.
We're better for one more.
Let's see, 1 cycle. So then 1 cycle is 1/60th of a second, right?
Yep.
Which is 1 over 60. One 60th of a second. Also called the period. So if I was given the hertz, you have a key on your calculator that converts it to time. And that is the x minus 1 key. So 60 hertz, x minus 1, equals
0.0167.
and if we took, let me see, 60, x minus 1 equals times 60 equals 1. So that works out. So it's 1/60th. So to convert one to the other, it's x minus 1. Let's see, common, let's see. Common aircraft. I think AC is 400 hertz. Hertz is what?
Frequency.
Frequency, cycles per second. Can range from 360 to 800 hertz.
Big difference.
It is.
What is the reason for that?
I believe now they're even getting into changing frequencies. It's not even set. It's like variable.
Well, in the
Can
sense
you
of,
already do that with a radio?
Yes, the whole thing is a radio.
well, what is the
Um,
reasoning
Or
for
they adjust
such a
by
high
power
frequency
for
is
the
more of what I'm kind of.
Oops. Hang on. What is the reason why they changed it? I honestly
Well,
don't
no,
know.
Why do they run at such a high frequency? At
More power out of it.
Okay.
More power pulses.
Owl, maybe.
More power. One cycle may also be referred to as a wavelength. One cycle may also be referred to as oops. One cycle may also be referred to as a wavelength. Amplitude is the peak value. So the highest point on it is peak value. Then we have peak. We have peak to peak. Kind of want to do it like this. All right, so this right here, that is peak. From here to here, that is peak to peak. Peak to peak. When you're looking at this, just to make sure we're clear, this right here will be your volts, or you can measure amps this way too. So that is how many you're measuring. This way is time. Just like we're looking at this. I went from 0 up to how many volts? 1 volt. And the time is, well, it's kind of hard to tell because it's like right in the middle of everything. So I don't know. It's one thing I don't like about this. If you don't reset this to 0 or something, it kind of screws you all up. Let's see, go back to here. Oops, schematic. And I have this set for 1 volt, and that is why. Frequency, I have it set at 1,000 hertz. We could set it at 60 hertz. And then go back to our grapher and take a look at it, and that changed it a lot. So got to bring it in so we can actually see a waveform. And then we would, that's 10 volts per division. So we would look at, this is more of what you're going to see on the oscilloscope. So how many volts do I have peak? 1 volt. How many volts do I have peak to peak?
2.
2. And what is, how long is each? It's a little hard to tell. What's my frequency? And I told you, but could we measure it off of this?
Yeah.
And how would we measure it?
By going one.
How long does one cycle take? So one cycle starts here, and does it go to here?
No.
Next one.
It goes to here.
Yeah.
All right. So we would figure out how long that is. That's 1.7816 kiloseconds. That's not. Is that right? I've never done this run out here before, so.
If we wanted a better number, we would just have to set it to 1 hertz. 1 hertz.
Why am I forgetting? Oh, there it is. E third equals. Yeah, I don't know about that one.
So shouldn't it be 1?
It should be 1. Because I set it for, no, 1/60th. Because I set it for, that's 10 milliseconds per division. So that'd be 10 milliseconds. That'd be 20 milliseconds. So what I like to do, if you can do it, and I can't, is move. On an oscilloscope, you can actually move everything right and left. And that makes it real easy. So I would just line it up. And you also have a few more blocks right there. Let me see. Ah, there we go. That's pretty dang close. 2 milliseconds per division. So 1, 2, 3, 4, 5, 6, 7, 8. 8.3. 8.3? Okay. We have 8.3 milliseconds. 8.3 milliseconds. Let's see.
Wouldn't that be times 2, because you have 2 milliseconds per division?
Yes. For each one. So 8.3
16.6.
times 2. 16.6.
Yeah, and that lines up because you do 60 to.
Yeah, I got like 60. I didn't do the milli in there, but now change it.
Yeah, 16.7 milliseconds probably.
How much?
16.7
16.7.
Yeah.
milliseconds, because then it's 0.0167 seconds.
Okay.
And what's that?
Well, if we ended up with 8.3 blocks times 2 was 16.6 milliseconds is what we come up with. So 16.6 milliseconds. That is 0.0166 x minus 1 equals.
Just about 59 point.
Did you guys see what I did there? Yes, no? Okay. Can you count the blocks? How many blocks did I have?
8.3.
And every single one of those blocks counts for how much time?
2 milliseconds.
2 milliseconds. So it's 2, 4, 6, 8, 10, 12, 14, 16 point. That would be 17. So bring it back. That's like 16.6 right about there. Seconds. Okay, everybody follow so far? Okay. So I got 16.6. And at the bottom it said each block is worth how much? 2 milliseconds. So we ended up saying it took 16.6 milliseconds to do one wavelength. Follow? One full wavelength. From 0, not to this 0, we got to go all the way to this one because I go positive and negative. Follow? 16.6. I got to do the whole roller coaster. Got to wait till you puke. Can't get off till you puke. All right. That took how long?
16.6.
And my question is, how many hertz is that? How many cycles will you get for every second? It took 16.6 milliseconds to do one. How many of those do I get in a minute, a second? In a second. It's 16.6, that is 0.0166. Everybody agree that is 16 milliseconds equals 0.0166?
Yep.
Okay. Everybody follow so far?
Yeah.
Times 60?
X minus 1 key,
It's 60.24.
which is to say 1 over 0.0166. And what does it tell you?
60.241.
60.241 hertz. Got it? I just converted how long it took one cycle to how many I get hertz, cycles per second. How many will I get in 1 second? 60. Well, what if I said I have 120 hertz? I know it's break time. How long does it take for one wavelength?
You take 8.3 milliseconds.
I would do 120 x minus 1 equals,
Yeah. 8 milliseconds, 8.3 milliseconds.
0.008333. So that is 8.33 milliseconds. All right, take a break.